Okay, good. So the title of the talk is Sketching for M-Estimators, a unified approach to robust regression. This is joint work with Ken Clarkson. Okay, so the regression problem in this talk, we're just going to look at linear regression, which is a statistical method to study linear dependencies between variables in the presence of noise. A very simple example here is Ohm's law. The voltage is the resistance times the current, and we get a bunch of voltage current pairs, and we're trying to learn this line that best fits them, the unknown resistance. And throughout the talk, we'll see various definitions of fitness. And okay, so in the standard setting, you have one measured variable B, which was the voltage on the previous slide, and a set of predictor variables A1 through AD. On the previous slide, D was equal to 1, and it was just the current. And the assumption is that B and the variables AI are linearly related, okay, up to some noise. So what we have is that B is equal to x naught plus A1 x1 plus dot 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 AD xd plus epsilon, where epsilon is some noise which may be stochastic, or it may be worst case. And we're trying to learn these unknown coefficients, x naught through xd. By a standard transformation, we can assume this free term x naught is equal to 0. And now when we see n observations of this measured variable, we can just write this in matrix form. So we're given an n by d matrix A and a vector B. A is so n is the number of observations, d the number of predictor variables. And when you write it like this, the goal is just to find a vector x in Rd so that A times x and B are close under some notion of closeness. Okay? And throughout the talk, we'll consider the overconstrained case when n is much larger than d. We have many more examples. Okay? So we have a very tall thin matrix A. Okay, so what are some common notions of closeness? So probably the most used is the least squares method, where you try to find this d-dimensional vector x that minimizes the Euclidean distance between ax and b. Okay? And the optimal solution there is just the projection of b onto the span of the columns of A. And this has certain desirable statistical properties. For instance, if the noise that you're adding is ID Gaussian, then this is an MLE. This is the MLE for this problem. Another nice property is it has a closed form solution. So if the columns of A are linearly independent, then you can just write down the optimal solution as A transpose A inverse times A transpose B. Okay, and similarly, if the columns are not linearly independent, you can write down the solution in terms of the pseudo-inverse of A. Okay, what's another fitness measure that's used? So one is L1 regression. And here the only difference is you're trying to find a vector x that minimizes the L1 distance between Ax and B. Okay, the sum of absolute values of differences on the coordinates. Okay, and this is sometimes used because the cost is intuitively less sensitive to outliers than least squares, right? Because you're not squaring the distance, you're just summing up the distances, so you're not trying to fit the sort of outlying distances as much as you would for the least squares solution. And you can set up this problem as a linear program and also solve this in polynomial time. Okay, so those are two examples, but what about the many other fitness measures that are used in practice, which is the motivation for this work? Okay, so this motivates this concept of M-Estimators, which include as a special case the least absolute deviation and least squares regression problems. So we define a measure function, so just a function g from the reals to the non-negative reals, which is symmetric, and g of 0 equals 0. And g is non-decreasing in the absolute value of x. Okay? And we can define the M norm. It's not a norm, but I'll just call it that, of a vector y just to be the sum of g applied to each of the coordinates of y. Okay? And we can think about regression in this very general context of trying to find this vector x, which minimizes the m distance between ax and b. And as I said, least squares in L1 are special cases, right? I can take g to be the square function for least squares, and I can take it to be the absolute value function for L1 regression. Okay, so yeah. Stop me if there are any questions. So what are some other loss functions that are used in practice? So one is the Huber loss function, which is the following. So the Huber loss function, it looks like least squares near the origin. It's quadratic. But as you move away from the origin, it becomes linear. And it looks like L1 regression. Okay, so this is nice in the sense that and it enjoys the smoothness properties of L2 squared. I mean, it's differentiable at the origin. And it also enjoys the robustness properties of L1. So as you move away from the origin, you're not penalizing it with the square function. You're penalizing it just with the linear function, right? And it's it's smooth. It transitions at some point c from being quadratic to linear. And there are many other examples of M-Estimators, and a lot of them do have this similar flavor, that they look quadratic near the origin and they start looking linear as you move sufficiently far away. So there's the L1, L2 estimator. If x is small, then you can show that this thing looks quadratic, and otherwise it looks linear. The same thing for the fair estimator. There's also this notion of a Tukey estimator, which is a little bit more extreme. So it's quadratic near the origin, and when you move far enough away, it just becomes flat. This can be approximated by moving, when you're far enough away, you're, a very low positive slope estimator. So these are all quite similar. So I need to define, restrict the class of M-Estimators a little bit to state our results. And I'll say that an M-Estimator is nice if it has at least linear growth and at most quadratic growth. Okay, so what does that mean formally? So there's some constant depending on the function used to define the M-Estimator. So that for all numbers a and a prime, where the absolute value of a is at least the absolute value of a prime, we have that the ratio of g of a to g of a prime is at most quadratic, a over a prime squared, and at least linear times this constant c of g. Okay, so an M-Estimator is nice if it has this property. You can show convex function g satisfies this linear lower bound, and this is quite useful because
What's the motivation for having at least linear growth?
So oftentimes you want to optimize convex functions. Convex functions satisfy this property. We need it for the analysis, so that's basically those are the reasons that I have. So this Tukey estimator does not have at least linear growth when you move far enough away, but you can approximate it by, as I said, by a line which has a very low positive slope. The motivation for the other question, the other bound, so why do we assume that it's at most quadratic? So it turns out that any sketchable g satisfies the quadratic upper bound. And let me say what I mean by sketchable. So this is just an intuitive definition, which is that you can take a vector x and you can compress it and preserve its m norm. Okay, and you can compress it to a small number of dimensions. That's what it means to be sketchable. So more formally, there's a distribution on t by n matrices S, independent of x, for which for every fixed x, if I sample one of these matrices S, we have the m norm of S of x is within a constant factor of the n norm of x. Okay, so and what we want is this t to be a slow growing function of n. So S is this wide fat matrix. We're taking this tall thin vector x and we're computing S times x. We're compressing it, and we want the m norm to be preserved up to a constant factor. And it's known that if I have, say, if this is growing larger than quadratically, then actually t depends very heavily on n. So for instance, if it grows as the third power, then for any such distribution S, I need to have at least n to the 1/3. T needs to be at least n to the 1/3, which is often prohibitive. So the way the algorithms are going to work in this talk is we're going to sort of do a sketch and solve type solution where we take a regression problem and we compress it, and then we solve the compressed problem much more easily. And this is sort of why we need this sketchable condition for that to work. Okay. So now with that, I can state our results. So let n and z of A denote the number of non-zero entries of your input matrix A to the regression problem. The first result is the following. So for the Huber loss function, what we show is that there's an n and z of A log n plus poly d log n over epsilon time algorithm, which outputs a vector x prime, which with high probability satisfies the following relative error guarantee, that the Huber loss applied to ax prime minus b is at most 1 plus epsilon times the optimal fitting to the regression problem under the Huber loss. Okay, so the time complexity is almost optimal. It's near linear in the number of non-zeros of this matrix A. You need at least n and z of A time to achieve relative error. And then for this wide class of M-estimators, we also show the following, that in n and z of A plus poly d log n time, we can output an x prime so that for any constant factor approximation, we get with high probability that for any nice M-estimator, ax prime minus b in the M norm is at most a constant times the optimal fitting in the regression problem. Okay, so it's a very general result for any nice M-estimator, and here the time complexity is actually optimal up to a constant factor. The difference, though, is it works for any fixed constant c greater than 1, and the time here depends quite horribly on this constant c. So as c gets very close to 1, this blows up. It's exponential in sort of the distance of c to 1, or 1 over that. So it only works for fixed constant c larger than 1. Just to put these results in perspective, so for convex nice M-estimators, you can solve them with convex programming, right? But these are generally slow. So a generic convex programming solver will give you poly n d time, whereas we're really getting time that just depends on the sparsity of the input matrix. And also, I'd like to say that in some sense that our algorithm for nice M-estimators is very generic in the sense that you start with, it's universal in the sense that you start with an instance to regression and you compress it, and the compression is done in a way that actually doesn't depend on the choice of M-estimator. Okay, so after you compress it, you can then decide which M-estimator you want to use, and you can just solve the compressed version in a different way for that M-estimator. Okay. So let me briefly go over the result for Huber, which I've isolated here because I think this is an important special case, and then the general result for M-estimators. Okay, so how do you solve regression? So here is a very naive sampling algorithm. So I have this, I'm trying to minimize the M norm of ax minus b. One thing I can do is just uniformly sample rows. Okay, so we can let S be a matrix which implements this uniformly sampling of rows. It's a diagonal matrix where I have either 0 or 1 on the diagonal, and I throw away the 0 rows. I just uniformly sample a small number of rows, say something that is polynomial in d over epsilon, the small dimension d. Doesn't depend on the large dimension n. And I just solve for the optimal solution in this much smaller space. It's a d-dimensional vector, and I just plug it into my original problem, and I hope I get a good solution. Okay, so this is a terrible algorithm, basically because you can't really achieve relative error this way. You're going to miss very important rows. You can imagine repeating a row many times, and then having another row, And you sort of need x to depend on both rows. But if you just uniformly sample, you're only going to hit this repeated row many times. So this can't achieve relative error. However, there's a better algorithm, which is also sampling based. But it's based on so-called importance. Okay, so it's based on importance sampling of the rows. And this is called leverage score sampling in the literature. So what I'm going to do is, instead of uniformly sampling, I'm going to give you a much better distribution on the rows to sample from. So this will work for LP norms. So suppose for the moment m is just taking the value x, is the function x to the p. Then what it says is there are probabilities q1 through qn. So each of these is just a real number between 0 and 1. And it specifies the probability that you sample, qi specifies the probability that you sample the ith row of A together with the ith entry of B. The sum of the qi's is small. It's poly d over epsilon. So if I think of these qi's as sampling probabilities and I apply them to the rows of this regression problem, in expectation I'll get roughly poly d over epsilon samples, which is small. And moreover, these probabilities guarantee that if I solve this problem in the sketch space, that I get a 1 plus epsilon approximation to the original problem. So if I sample each row I independently with probability qi, and I form this matrix S, this associated sampling matrix, and I solve this problem, then I'll get a 1 plus epsilon approximation. Okay, so one question is, how hard is it to find this distribution, these QIs? So you can actually find all of the QIs very efficiently for LP norms in near input sparsity time. Just one thing to note is here S is not 0, 1 on the diagonal as it was for uniformly sampling. To make this an unbiased estimator, you should scale up by 1 over QI, where QI is the probability that you sampled. Okay, so what are these importance sampling probabilities for LP norms? Okay, so we can first ask, what is it for the standard least squares regression? So what it is the following. So I have this matrix A, this n by d matrix, and now take any orthonormal basis for the columns of A. Okay? Then what do I know about this orthonormal basis? So the squared column norms are all 1. Well, what can I say about the squared row norms? So these are called the leverage scores. The squared row norms, in general, you can't say too much. I mean, the squared row norms, of course, sum up to D, since the squared column norms sum up to D. The squared row norms are also between 0 and 1. And I just let qi be the ith squared row norm. And actually, you can show that this qi is invariant under the choice of orthogonal basis that you choose for this matrix A. And so if you sample according to these, then they sum up to D, and they provide this relative error guarantee. Okay, this is a known result. And there are generalizations to LP norms. So instead of least squares regression, if I look at LP regression, there's a generalization of an orthonormal basis to what's called a well-conditioned basis by Desgupta et al. And it's very similar in the sense that the qi are the pth powers of the p norms of rows in this notion of called a well-conditioned basis. Okay, so that's what they are. And yeah, so that's how you would solve regression where the loss function is the LP norm. And so how are we going to solve the Huber regression problem? So we can first show an inequality that for any vector z in Rn, its Huber norm is sandwiched between its 1 norm and 1 over root n times the minimum of its 1 norm and its squared 2 norm. Okay, this is just by a case analysis of looking at, it's just the case analysis. And so this suggests a very natural algorithm that what we can do for Huber regression is sample from a mixture of a distribution defined by the L1 leverage scores, which I just said that you can do this for any LP, and the L2 leverage scores, which were these row norms in an orthogonal basis. So if I let Qi1 be the sampling probability of row I for the L1 and Qi2 the sampling probability of row I for the L2, then I just sample from this mixture of these two probabilities. And I need to oversample by a root n factor to compensate essentially for this loss in the inequality. But it doesn't matter because what happens is the following. We just get a very simple recursive algorithm. So our algorithm for the Huber loss function is the following. In the first step, we sample according to these probabilities, and the number of rows decreases to something like root n times poly d over epsilon. Okay? And then we just repeat this. So we then recursively solve a weighted Huber. There are weights involved in the recursion because you need to multiply by 1 over the probability that you sampled a row. But these weights don't grow too quickly. And once you do the recursion enough, where the number of rows is less than, say, n to the 0.01 times poly d over epsilon, at this point, the generic convex programming algorithms become efficient. And at this point, if I run a convex programming algorithm on the weighted Huber problem, it'll fit in my time budget of n and z of a log n. Okay, so that's the basic idea there. Let me just briefly say the result for nice M-estimators. So this is based on sketching instead of sampling. What we previously showed was that for L2 regression, we can do the following. If we take our matrix A and we compute S times A, where S is a random matrix of a very specific form. So S is a very sparse matrix. The columns are chosen independently. In each column, I choose the location of a single non-zero entry uniformly at random. And in that location, I put 1 or minus 1 with equal probability. Okay, so because it's so sparse, you can compute S times A in n and z of a time. And what we showed is that if you take roughly d squared rows in S, then if you replace A with S times A and B with S times B, and then solve the regression problem in this much smaller space, that you get a relative error approximation. And solving it in the smaller space only takes poly d time. So we build upon this result. And for general M-estimators, our sketch looks like the following. So it's a block matrix. What is this matrix? So in each block, I have Si times Di for some random matrices Si and Di. The Si are just independent count sketches that we saw on the previous slide. Okay, they're just these very sparse 0, 1, minus 1 matrices. And Di is just a diagonal matrix. Okay, so what Di is the following. It's an n by n matrix, right? I'm applying this to an n by d matrix A. Di is an n by n diagonal matrix. And on the diagonal, it's 0 or 1. And it's basically what it does is it just samples uniformly roughly a 1 over d to the I fraction of the rows. Okay? So the top matrix, D0, is just the identity matrix. Then D1 is the identity, but I zeroed out all but a 1 over d fraction of the ones, and I continue this process to get D2, D3, etc. And this is the whole sketch, which doesn't depend on your matrix A. You just compute. So let's call this sketch T. You just compute T times A and T times B, and you solve the regression problem. So what I said earlier about the sketch being universal is the following. So you compute T times A for the sketchy matrix T and T times B, and then you can choose any M-estimator. And what you do is you just solve this regression problem, minimize the M norm in the sketch space. And this is very efficient because the number of rows of T is something like poly d times log n, right? So whereas the original number of rows was n. Okay. This sketch comes up in various places. So it was used for estimating frequency moments in the streaming literature and for embedding Earth mover distance by Verbin and Zhang. I just want to note that many analyses of this data structure don't quite work because in contexts such as frequency moments, they sketch a problem and they reduce it to a smaller problem. But the smaller problem, in order to, when you solve it to try to estimate the original problem, you have to solve a non-convex problem. So it's very important here that in the sketch space, we're still solving a convex problem if the original problem is convex. And this gives us efficiency. And we show here that it works in the context of lopsided subspace embeddings, which, yeah, how much time do I have? I'm out of time. Okay. So yeah, so let me just say one word about lopsided subspace embeddings, which is that we can't preserve the entire column space of A. So what we'd like to do is, for all x, preserve the norm of ax minus b, which is preserving the norms of everything in the column space of A adjoint B. We can't do that, but what we can show is that this matrix T doesn't contract anything in the column space of A adjoint B. And for the optimal vector, it doesn't dilate it by more than a constant factor. And that's enough for the regression problem. It's lopsided in that sense. Okay, so let me just conclude. So in summary, we give input sparsity time algorithms for Huber loss function and for nice M-estimators more generally. Follow-up work and other questions. So we have some recent results for low-rank approximation. So typically when one does the singular value decomposition, one is interested in minimizing the sum of squares of distances. What we can do is minimize the sum of an M-estimator applied to the distances. This is a much more broad class of low-rank approximation problems. And sort of a meta question that was a question I had in my introduction earlier, which was that there are many techniques in sketching and streaming that have been applied to linear algebra to achieve faster algorithms. So count sketch gives input sparsity time algorithms for L2 regression. P-stable random variables, such as Cauchy random variables, are useful for LP regression, say for L1 regression, or more generally LP regression for P between 1 and 2. The approach here that we had is sort of based on what's known as count sketch plus finding heavy hitters in the streaming literature. And there are other techniques in streaming which give rise to sort of kernel variants of regression. And I think there's really a nice interplay here, and that remains to be explored more. So that's all.
Let's thank David. One quick question. Otherwise, I suggest that we'll take a break until 11:20 and maybe encore and can already maybe try to set up. Okay, thanks a lot. Thanks.